Hi everyone, we're going to take a look at transverse waves in this video. Now transverse actually refers to the motion of the medium compared to the motion of the wave. Now if you recall, a medium, that's just the matter through which a wave moves. And what you need to remember is that the matter itself doesn't actually get shifted out of position. What I mean by that is it vibrates, but once the wave goes by, it goes back to its initial position. So if we think of matter as made up of a whole bunch of atoms, like a solid, okay, then essentially what happens is a wave comes through this way, and that bumps this atom up, and then it vibrates back down. And so this atom just vibrates up and down, up and down, up and down. But because this atom got bumped up and it's got an attraction to this next atom, it pulls this atom up, which then pulls this atom up. But then because these atoms down here are still attracted to this, it bumps back down. And so you get this wave that has crests moving this way and particles moving this way, and that's what transverse means. Now what's cool about this is this connection between particles is what leads to the propagation of a wave. But if you were paying super close attention to this, you'll notice this isn't going to work in a liquid or in a gas, because in a liquid or a gas, the particles don't really have any attraction that's going to restore them back to where they were. There's no restoring force, if you will, to put this particle back. These ones will just flow in, and so there's nothing to pull up that next particle. So when a transverse wave hits a liquid or a gas, it doesn't travel through it. They don't propagate through that. Now, let's also take a look at some parts of a transverse wave. If you'll recall, we have a wave train, and essentially that dashed line in the middle would be the rest spot. Once the wave passes by, once this energy source passes by, the matter will return to there. Just like in simple harmonic motion, a wave motion, this is an amplitude. These are called crests. The top of that motion, that's a crest. The bottom is called a trough, and that distance is also an amplitude. Now the distance from one identical point to another identical point is called wavelength. Now wavelength is given the symbol lambda, lowercase lambda. That's wavelength. It does not have to be crest to crest like I just drew it. It could be any two identical points. So this is where the wave is cycling up, and this is where it's cycling back up again. So this could be one wavelength. Crest to crest could be one wavelength. Trough to trough could be one wavelength. But you could also pick this little down cycle to this little down cycle. Okay? It doesn't matter as long as the points are identical. Waves also have a speed and a frequency, and these are two different things. Remember, frequency is the rate at which something vibrates. This is waves per second. Essentially, if you could zoom in on a wave passing by like a ship's window, and all you saw was the water moving up and down and up and down, and you didn't see the motion of the wave going this way, then you would be looking at the frequency. You'd be looking at that up and down motion. Okay, so I just said that these waves couldn't propagate through water, and then I said a wave in water. On the surface of water, since the water particles at the surface are attracted to the other water particles, you can get what's called a surface wave, and it does look like a transverse wave. Okay, so frequency in waves per second, you could see that. That's the up and down motion. Now velocity is actually equal to the distance this wave travels in a given amount of time. So if we look at one crest and how far it goes, that would give us, and divide that by time, that would give us the wave speed. So this is distance, just like anything else, change in position divided by time. But in a wave, this is pretty cool because we know frequency is equal to waves per second. But if we invert that, then period is equal to seconds per wave. And we know one more thing. Okay, so I want you to think about this. Here's a wave, and it's traveling this way. Okay, now if we think about this crest, it's actually going to end up over here. Oops, it's going to end up over here in the amount of time it takes this wave to vibrate up and down one time. So this crest ends up over here. It's been down and back up. So that means it's traveled a distance of one wavelength it's taken a time of one period, capital T, which means we can say the velocity of a wave is given by the wavelength divided by t. And just to make sure that that makes sense, wavelength is a distance measured in meters, time is a second, period is a time measured in seconds, so that is meters per second, so our units check. And then since we know t is equal to the inverse of frequency, we can say, all right, that means v is equal to wavelength divided by 1 over f, which is just times f. So we have this equation for the speed of a wave. V equals wavelength times frequency.